So today we're going to learn a lot about heavy-duty natural gas engines. A little outline is going to come up here on the screen. Here we go. Three subjects we're going to start off with are at a very high level, a 30,000 foot level. What are the unique characteristics of a heavy-duty engine in general? Forget the fuel. What makes a heavy-duty engine a heavy-duty engine? And then, how are we going to get there with natural gas? All right, we can get there with diesel today, but what particular are we going to have to do? In particular, we're going to have to do with natural gas to make it meet the characteristics of a heavy-duty engine. And then finally, we're going to talk about the trade-offs, the differences between running an engine of that type on natural gas or diesel. So, heavy-duty engines, what are they? They're efficient. Okay, you'll see me write a little sign like that, ADA, okay? They get good fuel economy. They don't burn a lot of fuel for the horsepower they put out. That's one. Two, they're durable. They last a really long time. So if you have a passenger car that'll make it to 150, 200,000 miles, that's pretty good, right? These guys are running that much a year, and they want them to last 10 years. 1,000,000 miles. That's the goal. How are we going to do that? There's a lot of things on a heavy-duty engine that are that over the years have become sized and scaled based on these first two things. Okay, and a lot of it has to do with heat rejection. So classically, a diesel engine has been very efficient. Well, if it's very efficient, that means it's taking all that energy in the fuel and it's putting it down the driveline to the tires. Okay, it's not sending a lot of it out of the radiator or down the exhaust pipe. Okay, that energy is going where we want it to go, to the tires. So, heat rejection, low. Okay, so if your heavy-duty truck had a radiator that was scaled proportionate to your passenger car, it'd be about the size of a small billboard. All right? Okay, that's not what you see. All right? The reason is because that truck is very efficient. So, kind of fast forwarding a little bit, if we're going to put a natural gas engine into a heavy-duty truck, we better be ready to deal with the kind of radiator that's already there. We better be ready to deal with the kind of heat that comes off the exhaust that they're used to dealing with. We don't want to have to make them add a bunch of heat shielding, grow their radiator size, grow their intercool size, and all those things. Durability. A lot of this seems to center around heat rejection. Okay? With almost everything in the world, the hotter it gets, the shorter it lasts. Okay? Whether it's electronics or bearings or whatever. It gets hot, it wears out. Okay, so we need to keep the temperatures in these engines low so that they can be durable. As soon as we get hot spots, it's going to cause problems. Now we can combat that a bit with materials and get better and better materials that'll last longer, but in general, that's kind of a universal theme of increasing temperature, decreasing durability. So what does a heavy-duty engine get? It gets about 7 miles to the gallon, 80,000 pounds going down the road, 7 miles to the gallon. So let's contrast that with your pickup truck, 6,000 pounds, getting 12 or 13 miles to the gallon. That's how much better these things are. They're really, really efficient. They're really, really good. Power density. Okay. What is power density? What does that mean? That means for given an engine displacement, you've all heard, you know, I have a 3-liter engine, I have a 4-liter engine, 9-liter, 12-liter. For a given engine displacement, how much horsepower can we crank out? That's power density. Okay. So we have a conflicting problem here. There's two ways to get power density up. We can either make tons and tons of torque, or we can spin that engine really, really fast. A lot of RPMs, okay? So power is proportional, that's what that little symbol means, to torque, that's what that little symbol means, times the engine speed, RPM, all right? So if I want to get the power up on an engine, I can turn it at 8,000, 18,000 RPM like an Indy car, or I can make it make tons of torque at lower RPMs. All right, so What that does is that puts us in a box. It puts us in a corner because we need efficiency. Okay, so just like heat makes things wear out, turning really high engine speeds uses up a lot of friction and wastes a lot of energy. Okay, so we can't get high efficiency on a reciprocating engine by twisting it at 18,000 RPM. That is not going to happen. And by the way, it's probably not going to last either. So heavy duty engines turn slow. Your car probably has a 5 to 6 to 7,000 RPM red line on it, okay? Maximum speed of the engine. Heavy duty engines, about 2,000. So if we can only twist it at 2,000 RPM, how are we going to get power out of this thing? We're going to make tons of torque, 3 times, 4 times what you're used to in your typical passenger car engine for the same power. So you might have a 400 horsepower engine in your car that's doing 6,000 RPM. The same heavy duty engine is going to be doing 2,000 RPM, and it's going to be making 3 times the torque that your engine in your car makes, okay? So big torque at low speeds is what's expected to get the power density up. That's going to give us efficiency because we're turning it slow, and it's also giving us the durability because we're turning it slow. Another thing that people don't realize is that in general, this is not always true, but in general, the more power you can squeeze out of a given engine displacement, when you're operating at a higher power level, the more efficiency you get. And it kind of goes back to the same friction equation. Okay, I've got some kind of a fixed cost for my friction. I got to pay that no matter whether I get a little power out of the engine or a whole bunch of power out of the engine. I'm paying kind of that fixed cost of friction, running the air conditioning compressors, running the alternator, doing whatever, it's spinning the fan on the radiator, all that jazz, right? That doesn't really change no matter how much power I'm putting out, okay? So if I just use a little bit of usable power above that, I'm still having to pay this huge fixed cost. That's not very efficient, okay? I want to milk a ton of power above and beyond that friction load out of the engine. So for the most efficiency, I want to run real high power levels, okay? So that's another thing to keep in your mind. So power and power density, heat rejection, durability, and efficiency. Those are the characteristics that make up a heavy-duty engine. Those are the things that separate it from the engine that you find in your car or your motorcycle or maybe even your forklift, okay? Another thing to note is the duty cycle that a heavy-duty engine is under. This is very, very surprising for most people. When you're driving your car down the road at, let's say, 50 miles an hour, Lauren, how much horsepower? What kind of car do you have? Let me ask you that. What kind of car do you have?
Honda minivan.
Honda minivan. Okay, it's kind of a barn door. Ought to be using some power, right? So you're going down the road at 50 miles an hour. What do you know the horsepower of that engine? I'm going to guess that's a 200 horsepower engine, okay? I'm just going to guess. What do you think your horsepower is in that minivan at 50 miles an hour going down the road?
50 miles an hour down the road, I would think it would be very low.
Give me a number. Throw a dart.
75 horsepower.
About 12 horsepower.
Okay.
About 12 horsepower. Okay, does that surprise anybody? That's crazy, isn't it? 12 freaking horsepower. 200 horsepower motor, 12 horsepower at 50 miles an hour, okay? Heavy duty truck rolling down the road, okay? Say it's got a 300 horsepower or 400 horsepower engine in it, okay? 50 miles an hour, about 120 horsepower, 130 horsepower, okay? So that's what I mean by duty cycle. You're using about 6% of your engine's capacity to get down the road at 50 miles an hour. Heavy duty truck's going to be using about a third of its capacity. Way 33%. So 5 times the load factor that's just on that engine all the time. Great for fuel economy, right? I just mentioned that. That's one of the ways these things get good fuel economy, is because they're so heavily loaded all the time. That helps, okay? But it sure makes it hard on that. If your little Honda engine was under that kind of stress all the time, it wouldn't last 20,000 miles. It'd be over with. So it's even a worse durability equation than it appears to be at the outside. If it was really loaded like a heavy-duty truck, it wouldn't last at all. So, any questions on this stuff? Does it all make sense? All right. So how are we going to get there? How do we build a heavy-duty natural gas engine? And why is it even a challenge? Why do we even want to talk about it? Why is it a challenge to build a heavy-duty engine of natural gas, and why are they diesel? Well, one of the reasons that diesels fit so nicely into heavy-duty environments is because they're naturally very efficient, okay? They run high compression ratios. A high compression ratio equals efficiency, okay? So that's already got an arrow in its quiver right there. They're lean combustion, okay? What that means is you got a lot of excess air in the combustion chamber and you're squirting kind of a relatively small amount of fuel in there, okay? So it's not a super hot environment when you actually finally light the fire in there, all right? That tends to yield higher efficiencies in general. The other thing is they run unthrottled. What the heck does that mean? We're going to talk about that a little later. But that means that the air path into the engine is unrestricted. There's no valve that stands in between the outside air and those cylinders. It sucks in it breathes as freely as it possibly can, okay? And sucking air in when you have a restriction uses energy, like a vacuum cleaner, it uses power, okay? So it's got 3 arrows in its quiver to help this, okay? We're going to find out that natural gas is not so blessed. Moving on, what are other things about natural gas? Remember, we're going to heavily load this engine. We're going to be making tons of torque, right? What does that mean? That's like standing on your throttle, okay? And not just in terms of engine RPM, okay? I don't mean high engine RPM. I mean wide open, full power kind of stuff. Guess what you become susceptible to when you really, really load an engine up, especially with a turbocharger? Knock, K-N-O-C-K, okay? Knock, detonation, pinging, right? So gasoline has what's called a very low octane rating. Octane is a measure of the propensity of a fuel to kind of ignite itself, all right? So in a natural gas engine, we don't want that to happen. Or in a spark-ignited engine, which we're going to talk about, we don't want that to happen. So you've all seen at the pump, right? You buy 87 octane, 89 octane, 93 octane. High-performance cars need that higher octane, okay? They want to knock because they're running high compression, they're running lots of turbocharger boost, something like that. They want to knock, and we'll get into all that in a little bit. Guess what the octane rating of natural gas is? 140, 150, okay? Awesome. So we need to boost this thing up, make it make tons of torque. And so we've got a fuel now that we can put in there that's kind of like super racing fuel. So if we tried to build a heavy-duty engine out of gasoline, fail. It's not going to happen, all right? Some people ask me, what about propane? What's going on with propane? Why can't we have heavy-duty propane engines? Propane's everywhere. I see propane in pickup trucks. Well, you can. You can make a heavy-duty engine out of propane. Octane rating, about 100, 110, somewhere in there. And we'll get into why that's. So that means you're not going to be able to make as much torque in the propane heavy-duty engine. So you're not going to be able to have the same power density. So you can build it. It's just going to be kind of a bit of a weenie, okay, engine. It's not going to be as big power, big torque as a diesel or a natural gas engine can be because of that octane rating. So I keep talking about turbochargers, boost. You've heard me mention that several times. One of the ways that you get torque out of an engine is you use a turbocharger to essentially amplify the displacement of the engine. All right, so if your car doesn't have a turbocharger on it, 3 liter, 4 liter, 6 liter, 10 liter, whatever, the torque capability of that engine basically scales with that displacement. So a 3 liter engine versus a 9 liter engine, it's about 3-to-1 torque, roughly, sort of, close enough, okay? Not very far off. I put a turbocharger on that 3 liter engine, I can make it make more torque at the same RPM as that 9 liter. I can triple its torque easily. So I can use the turbocharger to amplify the torque of an engine, basically amplify the displacement of the engine. So when you see a truck engine that's, say, 12 liters of displacement, that equates on a torque basis to about a 30 or 40 liter naturally aspirated engine. That's a big engine, all right? 12 liters is big to start with, 30 or 40 liters is really big. But on a torque basis, that's the kind of torque you're squeezing out of these things. Now again, you're doing it at low RPM, so the horsepower is not exponentially higher, right? So you've traded off. You're running a low RPM, so this part's low, this part's big. So the power on heavy-duty engines is not that much different than big car engines. I have a 365 horsepower engine in my Ford pickup, okay? Well, that's not a bad power rating for a heavy-duty engine in a big truck. But I'm generating that power at a whole different RPM range, okay, which is more efficient. Is that making some sense? Okay. So trade-offs, running a heavy-duty engine on natural gas versus diesel. We mentioned several things, but it gets a little more complex than that. Nobody really cares about the fact that the diesel engine is throttled or unthrottled. They just care about the effect, okay? What does it do to my efficiency? Nobody really cares that the compression ratio is different. Nobody really cares I'm squirting the fuel directly into the cylinder instead of pre-mixing it. They care about the effect. So some of the effects are some of the differences in heavy-duty natural gas versus diesel. NG versus diesel. 1, little lower efficiency. Okay, so slightly less efficiency. Okay? Where, when, how? All the time, some of the time? The truth is, at high loads, so as the horsepower goes up, they're not that different. Very small differences, okay? At idle, big difference, and we're going to talk about that in a minute. The heavy-duty natural gas engine is throttled, and that's magnified, or actually that's where it's the most, is at idle. 2, heat load, heat rejection, radiators, exhaust. It's a little bit more. Not a lot, but a little bit. Okay? Response time. So we'll call this foot pedal, because the throttle's not on a diesel. Foot pedal response. This is wildly misunderstood. Okay, this means, let's say you have a manual transmission. I'm guessing most of the people in this room still have driven a manual transmission. On a diesel, you can basically not touch the accelerator and let the clutch out very rapidly. And that diesel engine can very rapidly accept that load, okay, and not die. Gasoline engine, there's a little delay in its ability to make power. What order of magnitude is that? What are we talking about here? Are we talking about seconds? No, we're not talking about seconds. I would say a diesel's response, diesel response time delay or ability to respond is approximately, I'm going to say 20 milliseconds. Okay, really fast, 20 milliseconds, okay, 50th of a second. Natural gas, a good natural gas, an E-Controls natural gas fuel system, which is the best on the planet, no kidding, okay? E-Controls natural gas system is going to be about 70 milliseconds, okay? So 3.5 times, that's a lot, but still 70 milliseconds, okay? So about a 15th of a second. So not horrendous, but not nearly as good as a diesel. Diesels are really good. Cummins, current natural gas systems, 9-liter, 12-liter engines that are out there, I hate to even write this down, 700 milliseconds, okay? Okay, now we got a problem, right? Trying to let the clutch out on that, that's a problem. And we'll talk about that. So the perception in the world is, the perception domestically in the United States is that natural gas engines have a real problem with response, particularly with manual transmissions. And why? Because that's the engine that's out there right now, the 700 millisecond Cummins engine, okay? China, running E-Controls, drive them all day long with manual transmissions and doing really well. So we got a perception problem here in the United States because of a lack of a high-performance fuel system on natural gas. So these are some of the differences in running a heavy-duty engine on natural gas versus diesel. You guys have got to come up with some questions at some point. Anything? Anyone? There's only one guy that got that. Okay, Tim, I know one's right on the tip of your tongue.
Why the big delta? Why is there a huge delta between our system and the Cummins?
I'm going to show you in the next, when I erase this whiteboard, I'm going to show you. You're going to be able to see it really plainly, yeah. And it has to do with the fact that the diesel fuel is squirted directly into the cylinders and that the air basically free flows in versus the fuel on the natural gas engine is introduced way upstream and has to make its way all the way through the intake manifold down to the cylinders, and that time is where that 70 milliseconds comes from.
So the placement of the injection of the fuel and the transport delay is a lot longer.
You got it perfectly, nailed. Way better than I could have said it, yep. All right, Joanne, I know you have something. Okay, all right. Okay, so let's roll on to the next topic. Getting a little more technical drawing depth here. If what?
If the landscape today is largely Westport Cummins in the U.S.,
Mm-hmm.
and we want to expand into the U.S. market, how best do we foresee the opportunity?
What we're doing several things. So the question is, how do we get into the United States market and start showing everybody the advantages of the e-control systems, okay, for heavy-duty natural gas? And what we're doing is we are currently in the process of buying an 18-wheeler tractor with a Cummins engine in it. So we're going to start out simple, okay? So that truck will come to us with a natural gas tank package, ready to roll, running on natural gas. And what we'll do is we'll go into that engine, and we're going to take the Cummins fuel system off of that engine, put our CFV system on, which we're going to talk about later. What is a CFV? We're going to put our engine control unit on there, and we're going to have it where it can switch back and forth. And so if a PACCAR, Navistar, Volvo guy comes in here, we can take them out back, let them drive the tractor both ways. By the way, it's going to have a manual transmission on it, and let them experience the advantage. And that's going to include doing some efficiency analysis on the thing so we can show them improved fuel economy, improved emissions, and better drivability. So that's how we plan on getting penetration, selling penetration into the market.
What is the diesel more efficient than compression ratio?
It's those three things I mentioned at the beginning. A diesel's compression ratio is going to be higher. That's one. It's unthrottled, so it doesn't have to do any kind of vacuum cleaner work against a throttle. That goes to it. And the third thing is overall lean combustion. So that's a very efficient form of combustion. And we're actually going to talk about that here in a second with natural gas. That's how we're going to get some efficiency on that natural gas. Okay. Anything else? No. All right. So, three things: fuel systems, ignition systems, and what that looks like globally today. Who's using what? We're going to cover kind of all variants, all reasonable variants, and then we're going to talk about what's the most popular and what's in use today from a fuel system and an ignition system standpoint. What the heck's a fuel system? A fuel system vocabulary for a fuel system to me means I've got the fuel up in the engine compartment from some tank package on the vehicle somewhere. How am I going to get that fuel down into the cylinders on the engine? Okay, that's what fuel system means to me. Okay, and that also encompasses whatever controls are in the ECM, the engine control module, to make that happen, and all the whole ball of wax there. Ignition system, what the heck's an ignition system? Once we get that fuel into the cylinders, how does it ever combust? How does it start burning? Okay, we'll talk about some of that. So, NG fuel systems overview. So this is not our fuel systems necessarily, it's going to be ours plus others. What are the different ways we can do this? Well, there's two fundamental ways. First way is what I'm going to call premix. And the second way is I'm going to call this direct injection. Okay? So premix fuel. This means that I'm going to take the fuel. Let me draw a little engine sketch up here. This is the intake manifold. Okay? So this is the air coming in. And here's the engine block down here with all the cylinders in it. Okay? And I'll draw Just draw some little cylinders for you here. This will be a 4-cylinder engine. Okay. So, little schematic of the engine. Pre-mix fuel. Okay. We've got air coming in here. Pre-mix means we're going to put the fuel and the air together way up here. All right? Way up here. So the fuel's going to come in somewhere up here, and they're going to combine together, and you're going to have an air plus a fuel mix all inside the big intake manifold that feeds all the cylinders. Okay? Direct injection. All diesels are inherently direct injection. You can't freaking do this with a diesel. It doesn't work. Okay? So all diesels spray. So I'm going to draw a little diesel injector here. They spray the fuel directly into the cylinders. Okay, so it's pure air coming in here, and then you're going to squirt a little fuel inside the cylinder at the last minute. Okay, that's direct injection. So there's 2 ways to do this. What are the disadvantages and advantages of each type of fuel system? The air and the fuel premix, as you can imagine, you've got plenty of time to get those guys really, really homogenized, okay, mix mastered on the way in. So by the time that mix gets down into the cylinders, you've got a really homogeneous mix of air and fuel. Everything's well distributed. It's a very uniform mixture, okay? If I've got air, pure air coming in here, and I've got this piston going back and forth very rapidly, and I'm just doing a millisecond squirt of fuel in there while the piston's on its way up, not so good mixing, okay? In fact, you can't even really mix it. It doesn't even work that way. You can't get good combustion that way. So it turns out that a direct injected natural gas engine burns its fuel the same way a diesel burns its fuel. Let me just take a second to explain that. Diesel combustion is what's called diffusion flame combustion, okay? So what happens is, imagine this little injector right here squirting some diesel in, some liquid diesel, all right? So the piston's coming up, got nice hot air in there because of the heat of compression, and we start squirting fuel in. All right, what happens is the air is so hot that as soon as that diesel fuel squirts into that hot air, very shortly thereafter, it catches itself on fire. It starts to combust spontaneously, okay? And it's burning kind of like a flamethrower while that injector is squirting fuel, okay? So as long as that injector squirts fuel, you got kind of this flamethrower hanging out the end of the diesel injector, all right? Very, very different form of combustion than what happens in a premix situation, okay? That's called diffusion flame combustion. So you got these diffuse flames coming out the end of the fuel injector. This type of combustion is premix or homogeneous combustion, and it combusts based on the movement of a flame front inside the cylinder, which means it's like throwing a match into a combustible tub of gasoline vapors, and it kind of does its thing, okay, uncontrolled. The diesel combustion is very controlled. Remember, it only lasts as long as the injector is squirting fuel. It only burns as fast as it feeds fuel in. The other thing is kind of like a fire and forget situation. Okay, so pre-mix, we're going to put a combustible mix of fuel and air together. There's no ignition source, so it doesn't blow up, it doesn't go off. It gets sucked into the cylinders, okay? Then the intake valve closes, you got a closed compartment there. Again, coming up on compression, you get all this combustible mixture, it's nice and mixed. You get up on compression, and then something's got to light it. It will not ignite itself because the octane of natural gas is so high, okay? The octane of diesel is like 0. It's not really 0, it's extremely low. But that heat of compression is not enough to light this stuff. Spark plug, that's where spark plug comes in, okay? Spark plug will light it, and then once that spark plug lights some of the mixture, the flame front sweeps through the combustion chamber all by itself, kind of on autopilot, okay? Uncontrolled. We have no control of it at that point once you turn it loose. So very different combustion. Direct injection natural gas is just like the diesel combustion, okay? So I'm going to have an injector inside of that cylinder. I'm coming up. I go to squirt the natural gas in. Only one problem, it doesn't ignite. The octane is so high, it doesn't burn like the diesel. So in addition to squirting the natural gas in there for direct injection, I've got to have an ignition source to kind of get it going. Once I get it going, it'll self-propagate, okay? Yeah, so you can put a little, you can squirt a little diesel in there in addition, tiny amount. Boom, it combusts. It lights the natural gas coming out of the injector. Now you got a flame that's going to continue to cause the additional natural gas to combust. After that, it looks just like diesel combustion. Okay, but you got to get it going. You got to kickstart it. So really, the only difference between a direct injection natural gas and diesel combustion is that you got to have that kickstart. Diesel can kickstart itself. This, you got to have something, okay? Premix, fundamentally different in every way. You've got an uncontrolled combustion event that happens once it makes it into the cylinders. Okay. So, premix, let's break that down, okay? There's not just one premix. We can do lots of forms of premix. We can do what I'll call air-fuel mixer. We can have continuous flow. Continuous flow mass control. And we can have what I'll call pulse width modulated. It's a fancy sounding word. Mass control. Okay, three forms of popular forms of premix, okay? So these three guys represent three different ways to accomplish this box right here, okay? Let's talk about one that may be the simplest to start talking about, continuous flow mass control, okay? So this engine's breathing air in because these pistons are going up and down and they're sucking air in, okay? And what we're gonna do is we're gonna take a device that's essentially like a garden hose gate valve, all right, under automatic control, and we're gonna continuously flow in fuel at a rate proportional to air that we like, okay? And we'll talk about that in a little bit, what that proportion should be. But that's all a continuous flow mass control is. If I got 100 pounds an hour of air flowing into the engine, I may want to have, let's say, 8 pounds, 7 pounds an hour of fuel going in there to match that airflow. I've got a device that just sits there and opens up just like a hose pipe or a gate valve on a hose pipe and just lets 7 pounds of fuel an hour to flow in there. And they just flow in together continuously and they mix and they go on down. Very simple concept. Very simple. Pulse width modulated mass control. Same fundamental concept, except it's not just a hose pipe valve that we open up and let flow 7 pounds an hour in there, okay? It's actually clicking on and off at a pretty high rate. So it's going from 0 to something pretty fast and then shutting off again. But on average, it's still gonna flow 7 pounds an hour, okay? But it's gonna be clicking on and off. So that's what pulse width modulated means. It's on for a while and it's off. Pulsing, okay? And the width of that pulse determines how much flow, and the frequency of that pulse determines how much flow we're going to get into the engine. So guess what? All of your cars in the parking lot, 100% of them have pulse width modulated flow going into your engine, okay? They're doing it with gasoline. They're doing it with a liquid fuel. And they're actually not doing it way up here anymore. They used to in the 80s. This is where everybody put the gasoline in. Nowadays, they're putting it in down around this region, okay? Still in the intake manifold, most of them. But now they've moved from here to here. Not a big difference. We'll talk about it. But they're doing that with gasoline, okay? You can do the same thing with a gaseous fuel, with natural gas. It's just a bigger injector. It's got bigger holes in it to let the gas through in the right proportion. That liquid's much denser. Air fuel mixer, what the heck is that? Okay, it's a carburetor. It's really what it is. It's a carburetor. And a lot of people don't understand carburetors, so I'll take a moment to talk about that. A carburetor is a mechanical device that basically determines that same proportion I just talked about. Remember 100 pounds an hour air, 7 pounds an hour fuel? Okay, it's a mechanical device that fundamentally controls that proportion all the time, okay? So it's not an electronic thing that happens. So That's why we used to see carburetors on cars before we had electronic fuel injection. We didn't have the electronics to determine that proportion. We needed a mechanical device that would do that for us. That's exactly why a carburetor was conceived and built, was to control that proportion. And what we are doing, or what we have been doing to date, Generation 1, Generation 2, and Generation 3 of our gaseous fuel controls are based around this technology, except they're electronically augmented. Very, very highly electronically augmented, okay? So our EPR technologies, electronic pressure regulator technologies, are centered around the air-fuel mixer device. So there's a fundamental mechanical device there, and what we're doing is we're controlling the pressure of the fuel going into that device. Now, a normal carburetor, back in the old days when it was purely mechanical, it was built to handle one pressure and one pressure only of fuel coming into it. And it would deliver one ratio and one ratio only of fuel to air coming out of it, okay? But what we've done with the electronic pressure regulator concept is we've taken that mechanical mixer and we are now very quickly and very precisely moving that pressure of the fuel around that's going into that mechanical device. So effectively, the combination of the two has formed a big electronic continuous flow control machine, okay? But we've done it in a bit of a roundabout way. CFV, continuous flow valve, which is our 4th generation fuel control, is a direct mass flow control device that doesn't need the carburetor. It doesn't need the air-fuel mixer. That part is absent in the CFV system. The Cummins systems that are out there today, the 9-liter and 12-liter engines, use this type of flow control. It's very, very similar to CFV. Okay, the execution is pretty radically different, but the concept is identical, and it's been around a long time. The Woodward systems that are out there today, and some of the Bosch system that's currently in development, and some of the Chinese quote-unquote indigenous systems that are out there being developed, all use a pulse width modulated control device, okay? And we, of course, have tons of stuff on the road today that use EPR air-fuel mixer technology, but we're rapidly transitioning to CFV.
Are there issues with durability on the pulse width?
Exactly, Joanne. So the question was, are there issues with durability? And the answer is absolutely, absolutely. So remember our first whiteboard here, we talked about durability being a crucial characteristic of a heavy-duty engine, million-mile. So when you have things clicking back and forth, slamming into each other at a high rate, like is required on these type of fuel metering devices, you have an inherent wear-out mechanism. Okay? Now you can make it really good, but it's inherently going to wear out eventually. Okay? A continuous flow device like the CFV, you can effectively build the thing where there's no inherent wear-out mechanisms. Now, will it last forever? No, because we're not going to use perfect materials throughout the device. But inherently, there's no mechanism that's going to make it wear out. So that is the big problem with the competing systems in the world, is that they don't last 1,000,000 miles. So the very best pulse width modulated fuel injector that would be the basis of one of these fuel systems today is about a 150,000 mile device. Okay, remember these trucks do this about every year. All right, close to that. So if you want a 1,000,000 mile fuel metering device, fuel system, there's not really an option, which is why Cummins is using the same topology as we use today in the CFV. It's fundamentally no wear out mechanisms. Westport, okay, not Cummins, a lot of confusions there, okay, but Westport on their HD15, the forthcoming Volvo 13-liter, uses a direct injection system. They call it HPDI, high pressure direct injection. Okay. What's the HP stand for? High pressure, what does that mean? 3,600 PSI. So they're injecting the entire time the engine's operating. From the time you fill it up to the time its tank is empty, they're squirting 3,600 PSI natural gas into that engine, along with a diesel common rail fuel system with a very tiny injector on it to light that fire. Okay?
So they're dumping the liquid right out of the tank into the engine?
No. what they do, it's a good question, Lauren. Okay, so how do they get 3,600 PSI? All of these systems today run on LNG only, liquefied natural gas, okay? LNG exists as a liquid inside the tank. It's a thermos bottle. It's about 260 to 280 degrees Fahrenheit below zero, but it's not at high pressure. It's at about 100, 140 PSI, as low as 60 PSI. It's in the 100 PSI range, okay? So what they do is they embed a cryogenic high pressure liquid pump inside the tank. So this thing is sitting down in the minus 280 degree Fahrenheit natural gas inside the tank, and then they seal the thermos bottle up around it, and they run some hydraulic lines into that tank to power that pump. They got a hydraulic power unit that's outside of the tank that's generating all the horsepower that that pump needs. And so the pump inside that tank takes that liquid, not gas, it takes it in cryogenic liquid form, and it pressurizes that liquid up to a little above 3,600 PSI. Okay, then they put a back pressure regulator on that thing, and they let that thing come, they let it come to a gaseous phase through a heat exchanger at 3,600 PSI. So that's how they generate it. And then of course you got to run big stainless steel lines all through the vehicle, all the way up to the engine compartment, and hook all that junk up.
Failed the dependability study right away. Just
Fails a complexity study for
well,
sure.
Right off the bat, the complexity. But
Right, which means it's going to fail a durability study.
Right, it's just
Yeah.
so many pieces to break.
Yeah, it's like a space shuttle. I mean, it's got 200 million moving parts. I mean, the thing is just crazy, and that is why this is not a good technology, because we live in a world where economics ultimately rules, and so it's all about how can I get the job done for the least amount of money and have it last the longest time, and this is about the worst in those two axes, as you can imagine. So is this making sense? All right. Any other questions? All right. So ignition systems. What are we going to do with ignition systems? Let's talk about that. So we've got our fuel system in place, and we got to figure out how to light the fire. All right. So there's a couple of ignition system types out there, and when I'm talking about ignition systems, I'm going to talk about either liquid or spark. Okay. So we'll just start with spark systems, and we'll say liquid. Okay. Let's talk about this and get this out of the way. This is pretty straightforward, okay? So if you want to use a liquid ignition system, you can do it in one of basically two ways, all right? You can do what's called a micropilot, and we can have diesel, Diesel is going to be the liquid of choice, by the way, and what I'll call full authority diesel, okay? So going back to our example over here, we've got the fuel and air in here in some form or fashion, either through direct injection or through premix, and we want to light it on fire, okay? Simplest way to do that is if we started out with a diesel engine that had a diesel injector in it that could run full 400 power on the diesel system that was intact. The simplest thing was just leave all that there. Don't touch it. I've got a diesel injector already in the cylinder. Let's just mix some natural gas and air up in here and send it down the pipe, and when it gets in there, we'll just squirt a little bit of diesel in there, not a lot, and let that be our ignition source. Great concept. Not going to work. Okay, and I'll tell you why. It works. I shouldn't say it works, but economically, it's not a good choice. Let me put it a little softer. So one of the huge advantages of that is that if I run out of natural gas, I just run on diesel, full power, okay? No problemo. But here's where it gets to be a problem. To get clean combustion, to not have a bunch of soot and generate a bunch of other bad stuff that I don't want coming out of the exhaust pipe, to get the engine emissions certified, I can't really put more than about 70% natural gas into that engine. I got to run about 30% diesel. Let's just call it 1/3, 2/3. And that's the best I can do. At idle, I can't do nearly that well. Okay, that's at a high load point, all right? So full authority diesel, I can run at best about 1/3 diesel and 2/3 natural gas. Okay? So what does that do? Well, first it erodes my economic advantage on natural gas. I'm still paying full price for 1/3 of the fuel that I put in there. So I'm only able to realize my 2-to-1, 4-to-1, whatever you want to call it, price advantage on 2/3 of the fuel. Doesn't sound like a killer, okay? Not that bad. But here's the other problem. I got to pay for the full diesel fuel system on that engine. All the content that's on that engine that it takes to make it run on diesel, I got to pay for that, and then I got to pay again for the natural gas system. Okay, so I'm paying double for the fuel system, makes my engine cost more. Okay. The other big problem with this is that on the after treatment side, we've got an exhaust down here. I'll draw it coming this way. Boy, that's bad. Exhaust. Okay, so I've got an after treatment system that looks something like this. Okay, and this little puppy on a diesel is $6,000 to $8,000 these days for Tier 4. Okay, this has got all kind of complexity and jazz in it. It's got an oxidation catalyst, which gets rid of CO and hydrocarbons. It's got a DPF in it, diesel particulate filter, that gets rid of the soot. And then it's got an SCR catalyst and a urea injection system on it that gets rid of NOx, NOx. Okay? Very complex, very expensive. All right? And if I'm doing this, I got to have all that. All right? If I decide to not have to run diesel, for example, in my system, I can go to a much cheaper after treatment device. I can go to a 3-way catalyst that costs about 1/3 to 1/6 of what this cost, $1,000 to $2,000. So radically different cost savings there. In addition, I have 3 tanks on my system now if I'm running this. I got a natural gas tank, I got a diesel tank, and I also got a DEF tank, diesel emissions fluid tank, a urea tank to run this SCR system on this after treatment. So lots more cost and just more complexity, pay, all right? So, but I have the advantage that I run on full diesel. Cool, that's great. Micropilot. This is an attempt to solve a few, and I mean a few, of the problems with this system. What I'm going to do is I'm going to leave that full diesel system on the engine, but I'm going to take those big diesel injectors out that can run 400 horsepower on that diesel, and I'm going to put about 1/10 size fuel injectors back in there. Little bitty fuel injectors that make a really, really fine spray and make a little bitty squirt of fuel. Okay? That's what the micropilot diesel means. It's a pilot ignition, kind of like the pilot on your stove. It's a small flame, okay? This guy can run roughly 90% to 95%, and really more, 90% natural gas, okay? Okay, so now I've erased most of my disadvantage in taking advantage of my cheap fuel. I can run mainly cheap fuel in these. Guess what? That's its only advantage. That's it.
So I
And
can't get rid of the urea catalytic converter?
100% the same. Even that small amount of diesel, that small amount of diesel still makes soot, which you got to get rid of. And guess what I lost in doing this? Okay, I got back that I could take advantage of more cheap fuel, but guess what I lost? I can't run on diesel anymore. The best I can do with this injector, right here, this micropilot injector, is idle the engine. I can idle and keep my AC running if I run out of natural gas and wait for the tow truck. Okay? So that's the best I can do. So really, really bad idea. Really bad. Okay? Westport. That's Westport. Okay? Stinky idea. If you're going to do it this way. At least you can run on full diesel, you know?
Well, it seems like also that would be a much
You would think. The problem is when you go look at the payback, it's horrific. Yeah. So the payback on this is terrible. The payback on this today, because of all the complexity, is more than 4 years payback. Most fleet owners don't even hold their trucks for 4 years. They buy them and they get rid of them in 3.5 to 4 years. So they can't even realize a payback on this. This costs just as much as this. There's no difference in the cost. It's the same, okay? But I can't take advantage of cheap fuel. So my payback just went from 4 years to 6 years or 5 years. Bad idea squared in terms of saving money, okay? Not good. Very, very poor strategic thinking by the people that really thought this would work. If I'm in the trucking business, I got a simple goal in mind. I'm going to buy a truck. I'm going to pay some capital up front. I'm going to buy a truck. I'm going to burn some fuel in that truck for 4 years. I'm going to pay a driver to drive it around. I'm going to have to pay for some maintenance costs. And then I'm going to sell the truck and I'm going to get some money back. And then I'm going to do all that again. And the only thing that I get to collect money on during those 4 years is how many pounds of junk I haul. All right? So if I can figure out how to not have to run on diesel, and I can do all that equation way more cheaply, I'm a business, nothing but money. I'm going to figure it out. And if I can have a competitive advantage against the guy down the road, I'm going to figure it out, and I'm going to get all his business too. So it's pure economics. They're going to win ultimately. And you're right, this would have been a good bridge strategy, except you lose money. It's like, why'd you even do it? Just buy the diesel. Just buy the diesel. You'll never, it costs more money to do this. You'll never make the money back. So it's a silly proposition in the end when you look at the economics. So that's liquid. What I'm going to do is kind of break this back down a little bit so I can squeeze this other stuff on here. Okay. So spark. We talked about this a little bit. We're going to get the air and the fuel mixed up. We're going to get them down in here in the cylinders, and then we're not going to use diesel to light the fire. We're going to use a piece of plasma to light the fire. It's a little spark across the spark plug, just like the one you have in your car, okay? And we're going to do that by generating some high voltage. And that high voltage is going to jump that spark gap and cause a very hot core of plasma to be there that's going to be enough energy to get a little flame going, and then the flame's going to take over and kind of sweep through the rest of the combustion chamber by itself. Two fundamental systems here. One is called inductive, and one's called capacitive discharge. A lot of discussions over the years about which one is better, blah, blah, blah. Okay. One thing is for sure, one thing nobody will argue about. This one's cheaper. Okay. That's about where the no argument list ends. Okay. Everything else is an argument. But this one's cheaper. So 100% of your cars in the parking lot have an inductive engine ignition system or running gasoline. Like I said, economics always wins. Economics always wins. So there's not a single CD production car in the world that I know of. Capacitive discharge, oddly, shows up in almost 100% of gas compression engines. So these would be engines like Exterran or Midcon or JW is putting out there in the gas compression market in our gas production system segment. We make one. We make a standalone CD ignition system for those. And then, of course, EICS, Engine Integrated Control System, also incorporates a capacitive discharge ignition system. So why the heck is essentially 100% of that market running CD when all the passenger cars on the planet Earth are running inductive? There is an argument, and it is an argument, that this provides more durability. The spark plugs will last longer. So spark plugs wear out. You're blasting a piece of hot plasma across a couple of metal electrodes. Those electrodes vaporize a little bit every time you do that. And the combustion event kind of wears that metal down. They're thin, small pieces of metal. They get pretty hot during the combustion event. They wear down, okay? And there is an argument that with capacitive discharge, you don't wear the plug out as fast. These engines run 24 hours a day, 7 days a week, 365 days a year, and they don't like to rebuild them any more often than every 5 years. And they don't like to go out and change the spark plugs in them, okay? And so the reality is that they're probably a little bit right. And a little bit right probably makes economic sense. If they'll last 10% longer, 20% longer, inherently, that's probably worth doing. It's probably worth spending the extra money, because this for sure costs more money, for sure. The other thing you can do with this is this is probably the more important thing to talk about. You can much more precisely control how much energy you put into the spark with a capacitive discharge system, okay? This is kind of a fire and forget type deal, a bit. This one you can very precisely control that energy and change it. So if you only need a little bit of energy to fire the spark, you can do that with a CD and you can reduce your wear. And that's where probably the biggest advantage comes from in running a CD system. So what do we do today? We're talking about heavy duty mobile here. The Achilles heel of a heavy duty premix spark ignited natural gas engine, the Achilles heel is the spark system, the ignition system. Okay? Everything else works really, really well. Everything else. But the spark system wears out, which is not good. And it wears out at a rate of every 40 or 50,000 miles, which is not good. And in a lot of ways, it ultimately limits how much power, how much torque we can squeeze out of that engine, how much boost, turbocharger boost we can put into that engine. And that kind of determines how high efficiency we can run. It determines how high power density we can run. So a lot of those initial things we put up there that were important characteristics of heavy duty engines, we have a hard time achieving those because of limitations on the ignition system. Okay? So, State of the Union, inductive systems are what we do and have been doing in heavy duty on-highway natural gas engines all over China and to date. So every heavy duty ECM you go look at today that we sell has an inductive ignition system in it. The reason is the market was China, high cost sensitivity, cheap, okay? And that's the way they wanted to go. There was also an argument that this type of technology actually might be a little better at lighting a mixture that doesn't want to be lit. So if you have a mixture that's right on the hairy edge of misfire, that's a mixture that doesn't want to be lit, there's an argument that this is better at getting that mixture lit a higher percentage of the time, okay? It is an argument though. There's also an argument that this is better. So there's two reasons that we're running inductive today. We're running inductive because it's cheap and because there's an argument that it's probably a little better at getting hard light mixtures lit or lighted. We strategically will be transitioning to capacitive discharge on those systems. By the way, Cummins, in their 9 liters and 12 liters, and in effectively every natural gas engine they've ever sold in the last 2 decades, capacitive discharge, okay? So we're headed that direction. We feel like the precision of control and the ability to fire multiple sparks and do some other things and do some misfire detection algorithms that we've developed that are fundamentally based on capacitive discharge are worth the extra money, and we think we can sell that to the customer on a value basis. Okay, so inductive ignition. And CD, capacitive discharge ignition. I'll actually explain this one first because it's kind of more, it's more straightforward. So, you got a transformer, okay? Two coils. And you got a massive turns ratio, okay? This is called the secondary. This is called the primary, okay? Anytime you go across a transformer and you've got more turns on the secondary than the primary, you're going to be stepping the voltage up. We're going to increase the voltage, okay? So what we're going to do is we're going to take a capacitor here. Very simple system. And here's a spark plug over here. See if I can draw a spark plug. I'm always challenged to do this. Okay, so that's my spark plug over here. Plug. Okay, this is the coil. Okay, there's a spark coil right there. Here's my capacitor over here. I'm going to charge this capacitor up to about 200 volts. Okay? And then when I'm ready to fire the spark, I close the switch. That's the whole concept. Very simple. Okay? So I got 200 volts on this guy. I close this switch. Okay? I got current going here, and you actually got DIDT going on here. I got time rate of change of current rising in the primary. Okay, and so what I'm going to see when I do that is I'm going to see a voltage rise over here on this spark plug. That's a high ratio across this thing of what I'm doing over here on the primary side. Okay, so the current over here, here's time, here's current in the primary. Okay, that's primary current. That's current in this circuit right here. Time over there is, here's where I start, and I see the current's going to do this. Okay, so this is time 0, and this will be at spark fire. Okay, and the time scale here is roughly about 10 microseconds. Okay, that's from the time I close that switch to the time that spark finally jumps over there. Okay, the voltage. So this is V secondary, okay? This is the voltage on the plug over here, okay? Voltage on the secondary does the same thing. Looks exactly the same, all right? Then you get a fire right here, fire. Okay, and this is going to be approximately 25,000 volts, plus or minus 20,000 volts. Okay, so 25 kV plus or minus 20 kV. Okay? So there's the whole spark event. That's how it all happens. It's very straightforward. Okay? Very, very different on this side for inductive. Identical on that side. By the way, plots, this plot is identical, pretty much, for inductive. So here's inductive. Okay? I'm going to take primary. Take my secondary, and here's my spark plug again. Okay, and all I'm going to do, look how simple this is. You'll understand why it's so cheap now. Okay, I'm going to take 12 volts or 24 volts. That's directly from the charging system. Okay, battery. There it is. Very simple. Okay. Now, I don't really do it this way. I actually switch the ground side, but the idea is the same. Okay. But the way I work that switch is radically different than this. Okay. The way you work the switch here is when you want to fire a spark, you have this pre-charged. It's ready to go. It's got 200 volts on it. Okay. And when I'm ready to fire a spark, I close that switch. 10 microseconds later, 20th of a crank angle degree later, at low speeds, the spark fires. Okay? This is radically different. Okay? This pre-stores all the energy that you're going to put into the spark in this capacitor. So all the energy you're about to go dump into the spark is already stored in this capacitor before you start. Okay? This guy stores the energy that it's about to dump into the spark gap in this inductor. Okay? And then you release that energy to the right. So what you have to do when you're ready to fire a spark is first you close this switch, okay? So you close the switch, the current starts flowing, okay, and it builds up over time. And when it gets built up enough and you've stored enough energy in this coil, then you open this switch back up again. And that event with a transformer causes all the energy that you've built up in here, it has to go somewhere, and it goes this way, and it goes into the spark. So what happens is, Let me try to draw this out. Here's time. Here's primary current. Okay? So I'm going to say time equals 0. I'm going to start ramping the current. I'm going to close the switch. The current's going to start ramping up. Okay? And then I want to fire right here. Okay? Time scale, 2 milliseconds. 10 microseconds, 2 milliseconds. So I can't just arbitrarily close the switch right when I want to spark. I got to know ahead of time. I got to close the switch, wait a little while, 2 milliseconds, and then fire. Okay? The voltage curve over here on the secondary looks like this. So this is V secondary. Okay? I'm going to try to go this down here. Okay? The voltage on the secondary looks like this. Time scales are compressed. Okay, this is about 10 microseconds. Same as that. It's just like it's blown up. Okay? So when I open this switch right here, which is what's happening, that's what's causing this spark to fire, 10 microseconds later, 25 kV plus or minus 20 kV comes out the other side. All right? Okay, so now we've talked at a 30,000 foot level about a lot of things. We've talked about the engines in general. We've talked about the landscape of fuel systems and ignition systems and who's doing what, where, when, and how, and what the advantages are. We're going to drill down now and get a lot more specific and a lot more detailed. And we're going to get, in particular, we're only going to focus on E-Control's Innovation Controls components from the E-Control's line of products. And we're going to talk about the specific functions of all of those. So we're going to talk about the fuel system, we're going to talk about the ignition systems, we're going to talk about something we haven't talked about yet, which is boost control systems. Very important, integral part of a heavy-duty engine. Boost control means we're controlling the turbocharger. The turbocharger is essentially almost always present on a heavy-duty engine. Not always, but 80%, 85% of the time. And then we'll get into a few other sensors and actuators beyond those fundamental components. So I'm going to start with my engine. I'm going to try to put it in a spot that I can kind of expand over time. Here's the intake manifold. Here's the engine. Here's the cylinders. And first thing I want to talk about, one of the simplest things we can start talking about is the throttle. Okay, why do we need one and where does it go and what's the point? The throttle goes right up here at the top of the intake manifold. So here's an example of a throttle. And it has a butterfly inside. Okay, so this is kind of drawn on edge, but you can see what's going on there. So this can restrict the flow of air into the intake stream. Why do we need to do that? The form of combustion that we're going to use down in these cylinders is premixed combustion. Remember that? Remember we had diffusion flame combustion for diesel, and we have premixed combustion for spark-ignited natural gas engines. You cannot get a natural gas engine to idle and make full power by just controlling the fuel going into the engine on a natural gas premix combustion. You don't have wide enough what we call dynamic range, okay? So what I have to do is I have to restrict the airflow at some point when I want to make lower and lower power levels. I have to restrict the airflow to keep it in proportion to the fuel at some point. A diesel, you don't have to do that. A diesel, I can have a massive, massive amount of air. I can have full horsepower air coming into the engine, and I can squirt idle fuel quantity in there, and it'll run at idle fuel rate, at idle power rate. It'll sit there and just idle nice at 600 RPM. Okay, all I have to do is have a sufficient quantity of air to burn that diesel. Anything I have in excess of that doesn't really matter. Okay, can't do that with natural gas with premixed combustion. I will eventually hit misfire. Okay? So if I have my fuel and air too far out of proportion in premix, I can't light the fire anymore. I can fire the spark all day long and it will not burn. Okay? So that's why we have to have a throttle. You sit up there. And I'm going to put the fuel in either just upstream or just downstream of that throttle. And I can take my pick. I'm not going to do both, but I can take my pick. That's going to give it lots of time to mix as it heads toward the engine cylinders. So it's going to flow through here, and it's going to be mixing, and ultimately get inducted into the cylinders, and then we're going to light it. Okay? So our fourth generation fuel system is called CFV, Continuous Flow Valve. I'm going to talk about it first because it's really the simplest one to understand. Okay? Here's a CFV, and here's a little device we'll talk about in a minute. CFV, the sole purpose of this device is to take fuel into this port and meter it back out of this port at a controlled rate, electronically predetermined. Okay? So the ECM, the engine control module, is going to estimate how much air is flowing in here, and it's going to say, I need some proportion of that. Going back to our old example of 100 pounds an hour of air coming in, I may want 7 pounds an hour of fuel. It's going to tell the CFV, give me 7 pounds an hour. Okay? And it's going to control that coming out of this port. Continuous flow. I'm going to take that fuel, and I'm going to squirt it into this hole right here. Okay? And the airflow is going to come right through this big hole. All right? And they're going to mix together. So this guy is going to be controlling the fuel rate. It's going to just push it into this hole. And the sole purpose of this device is to be a mix master. It has no other purpose in life. Okay? It doesn't restrict the fuel. It doesn't control the fuel. It doesn't restrict the air. It doesn't control the air. The throttle does that. This thing is just a way to get them mixed together. All right? This, what name have we settled on for this?
Injection nozzle.
The injection nozzle is what we've settled on for this device. Okay? We're going to talk a little bit in a minute about our EPR fuel systems. And those use an air fuel mixer, and they replace the function of this device. But they do have an influence on the air and fuel mixture. This one does not. Okay, it has no control. In fact, the CFE doesn't even realize it's downstream. It doesn't care. It does what it needs to do. So let's talk a little bit about this proportion of fuel I keep mentioning. Okay. Premix combustion. We want to control this air to fuel ratio. And a lot of people are familiar with that term. AF, air to fuel ratio. Okay? A lot of people, if you've ever messed around with racing, probably know that the perfect, chemically correct, what we call stoichiometric air fuel ratio for gasoline is about 14.57 to 1 for gasoline. Okay? It's on a mass basis. So that means if I put 14.57 pounds of air in, I need to match that with a pound of fuel. Okay? That's for the stoichiometric air fuel ratio. That means chemically correct. That means not too much fuel, not too much air. Not too little fuel, not too little air. Just enough fuel molecules to find and marry up with every single oxygen molecule they can find, no more, no less. Okay? If you end up, after the combustion is over with more oxygen molecules, you're said to be lean. If you end up with more fuel molecules laying around that couldn't find any oxygen molecules to marry up with, you're said to be rich. Okay? And stoichiometric's right in the middle. So I'm going to define a term that we use all the time that's called the equivalence ratio. Okay, the equivalence ratio is a big fancy name for something that's very, very simple. And it's represented by phi. Okay, that's the equivalence ratio. The equivalence ratio is equal to the stoichiometric air-to-fuel ratio, the perfect air-fuel ratio, divided by the actual air-to-fuel ratio that we're running in the engine at any given time, okay? So we can go lean of that, we can go rich of that, we can add more fuel, we can add less fuel, more air, less air. Phi is the ratio of those two, okay? So when phi is greater than 1, I'm rich. When phi is less than 1, I'm lean. And when phi is equal to 1, I'm at stoichiometric. Okay? That makes sense? All right. And it really works on a percentage basis. So at 1.0, I'm dead on, 100% right on. If I'm a 0.8, I'm 20% lean. I got 20% excess air or 20% lack of fuel, whichever way you want to look at it. If I'm 1.2, I'm 20% excess fuel or 20% short on air, whichever way you want to look at it. Okay? So let's talk for a minute about what that looks like on a plot versus some other parameters. So this is phi on this axis, okay? I'm going to put a line right down the middle at 1.0, stoichiometric. 0.0 is over here on the left, okay? And let's look at flame temperature. Okay, this is going to be the temperature of the flame inside the cylinders once we light it with a spark plug, all right? The flame temperature at phi equals 1.0 at the perfect chemical combination is at a maximum, okay? You can't get a hotter flame than when you burn at the perfect stoichiometric mixture, okay? As you go lean, as you leave extra oxygen molecules unmarried, okay? They serve as what is called a diluent, a dilutant. We say diluent. They dilute the mixture down. Okay, they absorb heat. They're laying around. They don't participate, and they sit there and do nothing but absorb heat. Okay? Flame temperature drops. Okay? And when you go rich, same thing happens. Except now you got fuel molecules laying around not doing anything, and they're just absorbing heat. Okay? They couldn't find anything to marry up with. They just exist in that state and just soak up heat. All right? So the flame temperature goes down over here. What does that got to do with anything? Well, curious thing happens. Okay? The cooler my combustion occurs, the less NOx emissions I make once I get out past kind of a threshold over here to the left. Okay? So if I run very lean, not combustion, a bunch of excess air, 40, 35% excess air, I will have such a cool combustion event in here that NOx, that's nitric oxide, which by the way is either NO or NO2. That's why we call NOx. All it means is it forms one of these two constituents, okay? The formation of this happens at high temperature. So if I cool that combustion event down, these don't form. They never get up to a high enough temperature to form. These are controlled emissions. This is a big deal. This is a big part of our universe, okay? The other big parts of our universe are hydrocarbons and CO coming out the back of the tailpipe, okay? These are the only three we're really concerned about on a natural gas engine. Diesels additionally have to worry about soot, particulates coming out, okay? We don't have to worry about that. We don't make any of that. Got a nice clean combustion. So my flame temperature cools off in this direction, all right? And at some point, I have so little fuel or so much excess air, whichever way you want to think about it, I'm absorbing so much of the heat of combustion into these other free molecules that I don't have a self-sustaining flame anymore. It puts itself out. It's like throwing water on a fire, okay? At some point, just like that water soaks up that heat of combustion, all that excess air eventually soaks up so much heat of combustion it can't self-propagate. Okay, it's not a chain reaction anymore. That happens at about a 0.65 TSP, about 35% excess air, okay, roughly. Actually, it probably happens more like at about a 0.6, a little bit leaner than that. Okay, so guess what the place is where you make the least NOx? Right before you can't keep the flame burning anymore, okay? And the closer you can get to being almost putting the flame out, the lower this gets. All right, so here comes the entire first generation of everything we've produced for heavy-duty natural gas and everything that's on the road today that we've ever produced in China is all what we call lean burn technology. Okay? Lean burn. Okay, so that means we're actually running the engine at this fuel proportion right there. And the margin of error between where we're running and where the engine starts to misfire and can't produce power anymore is about 2 to 3%. It's very, very close to lean misfire. So we got to be really, really, really accurate at estimating how much air is going into the engine and proportioning the right amount of fuel in. Okay, if we screw that up by a couple of percent, the engine starts misfiring and doesn't run. Okay? Oh, and by the way, the sensitivity of generation of this stuff is really sensitive. So if you run about 3 or 4% rich of where you're trying to operate, you triple your emissions. It's exponentially, okay? So we got this little bitty band we're trying to run in. So you're starting to see now, so hopefully I'm starting to paint the picture of how important it is to control the ratio of these two guys going in. We got to be really good at estimating how much air is going in, and then we have to be really good at controlling the flow rate of the fuel to match it. And we got to pick that operating point just right for that particular engine across its entire operating range, all speeds and loads. Okay? So does that help kind of shape it up for you? Okay, good. So that's lean burn. Let me make a note. Here we've got an exhaust coming out. Okay, so here comes the exhaust. And the exhaust ultimately ends up in an after-treatment device. Okay? Back in the day, we didn't even have one on a lean burn engine, but then later we had some emission standards that were a problem with CO and hydrocarbons, and we had to go deal with those. Okay, so here's the catalyst. Okay. The catalyst in general is nothing more than a bunch of precious metals. Rhodium, palladium, platinum, okay? And the catalyst is magic. Okay, what it does is it takes these chemicals that want to exist in the exhaust stream. They don't really want to exist there. They want to do other things. They want to settle out in more stable forms of themselves, okay? So really this NOx, really this stuff, it really wants to become nitrogen and oxygen again, not NO. And this CO really wants to go to CO2 eventually, okay? And these hydrocarbons love to find oxygen molecules and combust with them and turn into water and CO2. Those precious metals in the catalyst help that stuff happen. It only really works, though, at high temperature. So when the temperature of these precious metals gets up there, magic happens. And all of these things find a way, or some of these things, find a way to go back to their more natural, stable states that are not considered to be harmful. So on a lean burn engine, okay, we got all this excess air going in the front end, right? We're running 35% excess air going in the front end. Well, that means all that air comes back out the back of the exhaust. You got all kind of free oxygen molecules running around in the exhaust, tons of them, okay? Not breathable, but it's still a lot of oxygen. The types of catalytic converters, the types of catalysts that you guys have on your cars are called three-way catalytic converters. They will not work when you got a bunch of extra oxygen laying around. They do not function. So all the precious metals that are in there, these oxygen molecules foul the whole process up, and they don't do hardly squat when they're running with a bunch of excess oxygen in them. So lean burn, how does that work? Well, we're getting rid of most of this junk by just running really, really lean. So we don't have to really clean up any NOx emissions at all in the exhaust pipe. Okay, and if that was the only thing that was measured by the EPA, we wouldn't even need any kind of catalyst. Okay, but we don't. We got three things: hydrocarbons and CO. We got to get rid of that stuff. Okay, so the kind of catalyst that we have to run for lean burn systems is called an oxidation catalyst. Okay, oxidation means we're going to add oxygen molecules. Read oxidation as add oxygen molecules. Okay, so we're going to add an oxygen molecule to the CO, and we're going to make some CO2, carbon dioxide. Big deal. No problem. Great. It's what we breathe out every second. The hydrocarbons, we're going to get it to find oxygen molecules and combust and make CO2 and water. Okay, great. CO2 and water. Great, no problem. So a lean burn engine controls NOx through the combustion process, being really lean, and it controls hydrocarbon and CO by putting an oxidation catalyst on the back end. By the way, an oxidation catalyst loves those oxygen molecules laying around. It uses them. It combines them with the CO and it combines them with the hydrocarbons. It's all good. Okay? However, it's not very efficient. An oxidation catalyst is not a super efficient device. The efficiency of the three-way catalyst that is in your cars is unbelievably efficient. It's in excess of 99% efficiency. So that means if you put 100 grams of this garbage in the front of your catalyst in your car, 1 gram will pop back out the other side. In fact, less than 1 gram. A lot of these things are running at 99.6% efficiency, 99.8, 99.4% efficiency. So you put 100 grams of crud in the front, less than a gram of all this stuff combined, it pops out the other side. Okay, oxidation catalyst, not so efficient. Decent, but not awesome. 80 to 90%. So that sounds like it's close to 99%. Not at all. 99% is 10 times better than 90%, right? If I put 100 grams in the front, if I'm 90% efficient, I get 10 grams out the back. At 99%, I put 100 grams in the front, I get 1 gram out the back. So 90 to 99 doesn't sound like a big deal. It's a massive deal. It's 10x, all right? So we're challenged here, all right? We're also challenged in that we're running in that tight little box that I talked about right off of misfire and right between making tons of NOx and trying to be perfect on the air-fuel ratio all the time, right? And if we go a little bit rich, we make tons and tons of NOx, and we go a little bit lean, the engine misfires and runs like crud. So we're very challenged on trying to make lower NOx levels through the combustion process. So we're challenged on lean burn. But we've been able to figure it out all these years and get it there and meet the current emission standards, all right? That highway is kind of coming to an end. We can't really stretch this guy any further into more aggressive emission standards that continue to come out. We need a new game. We need to change our game, all right? And so what are we going to do? Well, we're going to do something that ends up in the end looking very, very similar to what we're doing today, except for the fact that we get to put a three-way catalytic converter back here, just like it's in your car, instead of having to do this dual purpose strategy at kind of, weak efficiency levels, all right? So let's talk about that. But you're going to see that the challenge continues to exist of very tight air-fuel ratio control, and then we're going to add another complication on top of it. So, phase 2 of combustion technology for heavy-duty natural gas with E-Controls products is not lean burn. Phase 2 is stoichiometric cooled EGR.
What is
Well, I'm writing right at the top. Hold on a second.
the magic for air-fuel ratio on natural gas?
The magic,
To get this stuff?
about 16 to 1. It depends on the, natural gas is not really a defined fluid. Natural gas is what it says it is. It's natural. So it's whatever comes out of the ground. It's primarily methane. And so here in the U.S., if you go put a gas chromatograph on our pipeline back there, you're going to find out we got about 91% methane, probably. It's going to have a little bit of nitrogen, a little bit of CO2, and it's going to have a little bit of heavies in it, like ethane, propane, butane, heavier hydrocarbons. But it's primarily going to be methane. And so depending on all those ratios, you get a different number than 16:1, but on average it's about that. Yeah. So lean burn is going to stoichiometric, cooled, EGR. All right. So that's phase 2 of our combustion process, of our strategy for controlling emissions. Okay. So what we get to do with this catalyst is we want to make this one of those 3-way catalysts. Okay? One of those really awesome 99.4% efficient 3-way catalysts. Remember, we can't do that on lean burn because we got all those extra oxygen molecules running around. That fouls this guy up. So, what are we going to do? We've got to get rid of all the oxygen molecules. All right? Easy enough on your car. Just run here. That's exactly where the catalyst wants you to run. Okay? So if you run there at Stoic at 1.0, this thing works, and it's all beautiful. You get 99.4% conversion efficiency. One massive problem. I just went up this flame temperature curve. Okay? In fact, I'm running at peak flame temperature. I can't get any hotter. All right? So everything inside that cylinder just got really hot. And my poor exhaust valves, and my poor intake valves, and my poor turbocharger, and all of that just got really, really hot. And all the heat that gets transferred to the coolant out the side of the cylinder walls that ends up in the radiator, my radiator just had to get bigger. Okay? So go back to the original discussion, right? Heat rejection and efficiency and durability. Remember those 3? They were the fundamental characteristics. So I get to clean up all the exhaust, but I take a hit on 3 of my 4 primary characteristics that I have to have a really good heavy-duty natural gas engine. Now, you're driving your car around, you don't need those things. You got it, right? It's all good. You're running your 12 horsepower on your Honda going down the road, and you only need it to last 200,000 or 300,000 miles, and it's all good. So how the heck are we going to skin this cat? How are we going to get our cake and eat it too? How are we going to get to put this amazing piece of magic on the back end of the engine, reach lower and lower emissions levels, and at the same time have our engine last for a really long time and not have to have huge radiators and get really good efficiency? Well, what we can do is we can use something other than oxygen molecules to dilute this combustion temperature down that this thing doesn't care about. It doesn't like oxygen molecules, all right? But it doesn't mind other stuff, CO2 being the big one and nitrogen being the big one. To this guy, nitrogen and carbon dioxide pass right on through. Like it's like they're not even there. Okay? Well, if we're running here, right here at stoichiometry, guess what this exhaust looks like? Okay? When you're running at stoichiometry, stoic exhaust mainly, almost completely, is equal to the nitrogen that went in from the free air. We got 79% nitrogen in the air we're breathing right now. Nitrogen, we got CO2 from the combustion, and we got water from the combustion. Okay? And we got these guys too, but these are in microscopic trace amounts relative to these guys. Okay, so we got 79% nitrogen, we got whatever 20 some odd percent of this other stuff coming out, and we've got 100 parts per million or 500 parts per million of this coming out. So they're in microscopically smaller quantities. Okay, so this guy's perfectly happy swallowing this stuff, and guess what? That's what's available right here. So here's what we're going to do. We're going to take it, we're going to pipe it over here. Here's a cooler right here because this is hot, right? And I'm going to erase this. This is not going to be my fueling location anymore. Actually, I'm going to add another one here. This is my valve. EGR. Exhaust gas recirculation. You always want to know what that term meant. EGR. There it is. So we're going to take exhaust gas and we're going to recirculate it back into the engine. All right? We're going to cool it down because it's really hot over here, 1,500 degrees Fahrenheit. We're going to knock it down to a couple hundred degrees Fahrenheit or maybe cooler. We're going to put it through a valve so that we can control how much we're putting into the engine. And we're going to stuff it right back into the air-fuel stream. So we're not going to have air and fuel in here anymore. We're going to have air and fuel and whatever additional CO2 and water comes back through. Okay? And those molecules, these extra molecules right here, are going to go into the combustion chamber and they're going to serve now as the diluent, the diluent. And they're going to soak up the heat. And they're going to drive our temperature back down here. Okay? So we're going to stay here at stoichiometry, but we're going to traverse this curve this direction. This is increasing EGR. Okay? And we're going to drive that flame temperature right back down again by doing that. Okay, but guess what? All the same junk happens. I'm cooling this combustion process down, right? And at some point, I put too much of this stuff in, I don't have a self-sustaining flame anymore. All right? Flame goes out, misfire. So I can misfire by putting a bunch of extra oxygen in, eventually, or I can misfire by driving a bunch of excess EGR in. And guess where I want to operate, of course? I want to operate right off the misfire limit with EGR because that's when the combustion is going to be the coolest, and my exhaust valves are going to last the longest, and my turbocharger is going to last the longest, and my radiator can be the smallest, and my efficiency is going to be as high as I can get it. Okay? Because I'm going to be putting all that energy that I can back down the crankshaft. So I'm challenged in very similar ways from a fuel to air ratio standpoint, except now I have the additional challenge of making sure I put exactly the right amount of EGR in and run it on that point. Okay? But I have the massive advantage that the stuff coming out of this exhaust pipe now works inside a three-way catalytic converter, which is a piece of magic, beyond all pieces of magic. Okay? 99.5% conversion efficiency. And essentially what I have right here, depending on how much money I want to spend, I now have a knob that I can twist as low as I want to go. Okay? Before, when I was lean burn, I was constrained, right? At 80, 90% catalyst efficiencies, and hitting that perfect point in combustion to get the NOx down, I was constrained. I couldn't arbitrarily reduce my emissions. It's hitting a wall. I can now arbitrarily reduce my emissions. I might be spending $500 or $1,000 on that catalyst. I can decide to spend $1,500 on that catalyst and load it up with all kind of precious metals and make it really big. And I can cut my emissions in half or a third or a fourth or a tenth or whatever. I can actually literally clean the air with that catalyst. There can be more ambient NOx and CO in the room right now that this engine would breathe in. I can actually have the stuff come out the back of this catalyst be cleaner than the air it breathes. So that's how magical being able to use a three-way catalyst is. And that's why we want to go there for the future. The other big advantage is that we're starting to compromise fuel economy on lean burn by trying to get to those lower and lower emission levels. With this, we don't have to. With this, we don't have to. The fuel economy is strictly governed by how closely on the edge we can run with this EGR. Yeah, Joanne?
Do we call it an EGR valve, or do we call it something else?
We do. We call it an EGR valve, and we don't have one. That comes from the manufacturers. So what happened in 2004 is almost all the diesel manufacturers the world around started using EGR in their engines also. They started using these coolers and they started using these valves. And so they developed the technology almost 10 years ago for the diesel engines. So we get the incredible advantage of just being able to reuse what they've already developed on a natural gas engine. So that's a really nice thing that we can take advantage of. All right. Okay. So transitioning now to kind of getting away a little bit from talking about the combustion process and lean burn versus stoic EGR. We get a little bit more back into the components. one of the other things I did not draw in here, let's see if I can fit it in, is we want to be able to measure how much EGR we're actually flowing. Okay? So here's our cooler again. Okay, I've redrawn it off to the right. And then this little device is typically a little Venturi, so it's got a little restriction to it. Okay, looks a lot like the inside of this thing. See how the kind of goes in big, comes out small. So what that does is that causes a little pressure variation across this thing. And if we put a sensor here that can measure, that's pressure, a little P on there. We can measure that pressure differential across that thing. We can estimate the flow rate through there. So remember, we got to control this very precisely along with the air and fuel. So we want to be able to measure that EGR valve to control the rate, and so that's how we're gonna pull off metering that EGR flow in there. All right, I'm going to go ahead and erase this graph, make some room on here for some other stuff. Is everybody all right with that? Everybody got this? Okay. Give myself a little breathing room here. Okay, so let's talk about what else has got to go on here. Take the front of this job off. Okay, what's really going on here is we got a throttle, like I drew, and we got our CFV up here. Fuel's coming in here, and we're going to take it and we're going to squirt it in here. So here's our fuel, here's our EGR. This has got our little mixer on here, right? This is our, what do we call it, Chris?
Injection.
Our injection nozzle is right there, okay? We got our air coming in here. Here's our throttle. So what's really happening is there's a turbocharger out here. Actually, there's more than a turbocharger. There's a cooler out here. It's called an intercooler. Okay. And there's a turbocharger. There's an ugly turbocharger. Okay, then we've got a big air cleaner out here. Air cleaner, everybody knows what the air cleaner looks like. Big filter. Okay. So, there's the air path. Air comes in the air cleaner, goes to the turbocharger. This is actually the compressor end of the turbocharger. So it compresses the air up to a higher pressure. It's hot though. Anytime you compress air, you also increase the temperature. They go up simultaneously in a proportion to the specific heat of the, it's a power equation that they go up in. So you got real hot air here. You go through an intercooler, which cools that air back down, okay? Then you flow that cooler high pressure air across the throttle, past the fuel mixing, the injection nozzle, and then we have a very similar kind of a mixing device over here for the EGR, okay? So we're gonna get all that homogenized, all mixed up really, really well. And then we're off to the races inside of the engine, okay? Now, one of the devices we did not bring in here is an Envirotech. Envirotech sits right here, okay, Envirotech. It sits right there. And what it does is it measures the humidity in the airstream coming in. Why do we care? Okay, well, think about it. If we have dry air, No water molecules, all right? And we get all the way down in here and we get in the combustion chamber. We have only the EGR as a diluent. Okay, so only the stuff that comes back in that we let in this direction absorbs that heat of combustion. Okay? If we're in Thailand, okay, and it's 103 degrees outside at 98% humidity, relative humidity, there is a lot of water coming in the front end of this thing. Okay? On the order of 2 or 3% of the total mass of air coming in is water. That's a lot of water. Okay? And so that goes all down. Now all of a sudden, down in the combustion chamber, we've got all the stuff we've shoved in with EGR. But then we got all these other water molecules that are there too. Well, guess what that does? If we were running right on the edge of misfire with the amount of EGR we were pushing in, all of a sudden, whoop, we're in full misfire now because we got all these other water molecules absorbing the heat of combustion. Okay, it's just like putting in too much EGR. It's the same effect. So because we're trying to run right on the edge of misfire to get the best results from the engine, just exactly like we used to run there on lean burn technology, the water content in the incoming airstream is very important. Okay, and so that's why we make the EnviroTech sensor. So here's a piece of technology that we believe it has been very important for lean burn to date and will continue to be very important even for Stoic EGR engines because they have they're challenged with the same problem. Okay, the compressor, how does it work? Well, there's a similar device over here called the turbine that actually sits over here in this exhaust stream. I'm going to draw it as best I can. Okay, it kind of works in reverse. And let's realign this guy here. Okay, so this is the turbine. Okay, and this EGR stream is going to be picked off right here. Okay, so this thing is the inverse of this guy. This guy, the engine is pushing exhaust through this turbocharger, and it's taking mechanical energy out of that exhaust stream and spinning a shaft. This guy is connected to, is on a common shaft with this guy, and it's taking that mechanical energy out of that shaft and compressing air up. So they work in conjunction with each other. And by the way, it's important that I'm picking the exhaust gas off right here upstream because there's a big pressure drop across this guy. Under full load, you'll be coming out of here at 35, 40 PSI, and you'll be discharging into essentially ambient air conditions downstream. And so we need this pressure to drive the flow back in. We got to have that pressure to get it back in. Now, if you remember a long time ago, I talked about one of the disadvantages of a natural gas engine is that the throttle has to be here. And that throttle makes you do vacuum cleaner work. Okay, when we're pinching that airflow off, this engine has to work hard to pull that air through. It's pulling it against a restriction, okay? So it has to work hard to suck that air through. So what we want to do is we always want to minimize how closed this throttle is. All right? So when we're idling, okay, so we're sitting at a stoplight, we're not making any boost. Okay, this turbocharger doesn't have enough energy flowing through here to do squat. All right, it's just sitting there just kind of doing nothing. And so it's basically just like your car. All right? So this throttle, though, to make that small amount of power on that engine has to close way down. And there's essentially nothing we can do about it. All right, there's really not much we can do about it. We can feed some EGR back in, but that kind of runs out of gas quick. So we got to shut this way down. But when we start to power up, when we start to bring the torque level up, okay, and the airflow starts to go up and this turbocharger starts to work, we get up above atmospheric pressure. We're making positive boost now. We're building boost up above atmospheric pressure. Doesn't it make sense that we could just leave this completely wide open and just control somehow how much pressurization this thing was doing? Okay? So let's say that, you know, atmospheric pressure is around 15 psi, right? 14 point something, depending on where you are. Around 15 psi. So if we needed the flow rate that was the equivalent of 20 psi, why would we make 30 here and then close this throttle down to make 20 in the intake manifold. Why would we do that? That doesn't make any sense. Just go wide open with this thing and only make 20 with this, and you're done. And you got no disadvantage relative to diesel. Remember, diesel breathes completely freely. Diesel doesn't have this component, okay? Maximum efficiency, no vacuum work to be done. Well, what we try to do is exactly that, okay? And that's what these little guys are right here. These are our boost control valves, all right? So what these guys do is they allow the engine computer to come over here and modulate or modify how much boost this guy's making. And the way they do it is by opening what's called a wastegate over here on the turbine side, okay? The wastegate essentially does this. That's a valve, by the way. Okay? So if I open this valve up, I short circuit around this, I bypass all the gas going through this thing, so I don't put much energy in here. So if I don't put much energy in here, I don't get much energy over here, so this doesn't make as much pressure. Okay, they're coupled. So this is called the wastegate. Okay, that is not that valve, by the way. Okay? The wastegate is a thing that's smoking hot sitting on the side of the turbocharger that gets really hot. Okay? But what I can do is I can control this wastegate with that device. All right? So typically on most engines to date, but not all, this guy is operated with pressure, air pressure. Okay? And so this little dude, this little valve is typically hooked up to like this. And when this pressure gets too high, this thing opens. So, but it only does it at one pressure. Okay? One way. It's totally non-modifiable. If I insert this guy in between a pressure source like here or the compressed air that exists on all heavy-duty trucks to run their brake systems, then I can control the pressure that comes out the other side, and I can make this wastegate do whatever I want. I can electronically control this thing. All right? And so all of this is in an effort. Once we get off idle, once we get up and we start making a little power, all of this is in an effort to run this as wide open as I possibly can and only make as much boost as I need. Okay? It's for the maximum efficiency of the engine. Now, there's a problem, and it's a drivability problem. So if you were running this thing in a stationary application and you had 5s and 10s of seconds to change power levels back and forth, there would be no problem. We could open that thing wide open when we were up off idle and just change this boost level and it's all golden, okay, maximum efficiency. But when you're driving down the road, okay, and you got a foot pedal and you want to put your foot in and bam, feel some response. Remember that 20 millisecond response we wrote up there for a diesel? When you want to feel that immediately, this stuff over here doesn't work that fast, okay? This shaft that's spinning and the propellers, the impellers that are on either end have mass, and it takes a while for them to speed up and to slow down, okay? And it takes literally seconds, orders of magnitude, like seconds, 1, 2, 5, 3 seconds type response time. So if I'm driving and trying to shift, I'm going to be really hacked off, okay, when I'm waiting for power to come online every time. So what we choose to do is we choose to constantly make a trade-off. We choose to constantly get this thing pretty open, but not completely open at part power conditions, and run a little more boost than we need, okay? Because what happens then is when you put your foot in, I can then snap this open in milliseconds and get a bunch of a power increase right off the bat. Not all, but a bunch. So I can feel it in my seat. And then I can probably wait a little while to let this kind of thing spool up. So it's a big compromise we play. And we have systems in the ECM to do all of that. Does that make some sense? All right. This little guy. Nasty, nasty stuff happens if I'm making full power on this engine and this guy is spinning like crazy and making tons of boost and I'm running a full 400 horsepower and I take my foot off the accelerator pedal and I'm ready to shift, and when I take my foot off the accelerator pedal and this thing slams closed, nasty, nasty stuff happens, okay? I have a ton of energy stored in this spinning mass over here. This is spinning at 100,000, 125,000 RPM, this little wheel inside of here, okay? And I've got a bunch of air mass that's flowing at high velocity through there. And all of a sudden I go, wham, stop. Well, that sends a pressure spike. You ever heard of a water hammer? You ever heard of that effect? Okay, you ever heard it in your house? You turn a valve off in your house and you go, you ever heard that? Okay, same effect happens here. And it'll happen every time you shift. So tens and hundreds of thousands of times a year it would happen every time you shift. And so these huge pressure spikes happen in here. Every time you lift off the foot pedal when you're under full power condition. The job of this guy is to make that go away. All right? So what this little dude does, it's a purely mechanical device. Okay? And what he does is he sits here, right here, and he has a little sense line. It's just a sensor line that comes over. That's this little dude right here. Okay, comes over and smells this pressure downstream. And he's hooked up in a big way to this pressure right here. And what he does is he will take all of this, and wow, I can't draw a very good plumbing thing, but he will take it and do this with it. Okay? So, when you slam that guy closed now, okay, this guy can smell that you just are trying to create a big pressure drop across his throttle, okay? So this wants to go to very low pressures when you slam that closed, and this is going up to real high pressures because it's starting to water hammer. When it smells that, when it sniffs that, it opens up mechanically, okay? And it lets all that air that was initially headed this direction, it lets it divert and go that way. No water hammer. This is called a boost recirculation valve. Yeah, let me label that. Boost, I'll just say recirc valve. Okay. On a diesel, you don't need one of these. Okay. This can slam closed. There's nothing to slam closed. We don't use a throttle. But on a natural gas engine, you do. So why do we make this? Because nobody makes it for heavy duty engines. We had to come up with our own. It's not common in the diesel world. What were you going to say, Lauren? Oh, no? Okay.
I was just saying because the diesel loves air.
What's that?
I said because the diesel loves.
Oh, yeah, bring it on. Yeah, who cares? So that's another piece of content we have. So we have the EnviroTech, we have this guy. I'm going to draw a little line over here. And this is what we'll call our wastegate control valve, WGC. Wastegate control valve. Remember, that's this piece of content right here, this little dude. So it's controlling this wastegate on the turbocharger. So we've kind of mapped out most of the stuff that goes into the engine. The ignition systems we already spent a lot of time on. I'm not going to spend a lot of time on that. There are coils here with spark plugs in each cylinder. Okay, we already spent a bunch of time on that. The only thing that I'm going to spend a little more time on right now is the system here looks very similar for pulse width modulated fuel control devices. Remember that? Clicky injectors. It's just you replace this, our CFV, one of those. However, our first, second, and third generation systems, EPR systems, look a little bit different than this. So I'm going to start erasing a few things right in this section and draw that in, and then we'll be done with this section of the presentation. So before I do that, does anybody have any questions about all this junk we've accumulated on the board?
On the you talked about on the wastegate being causing the system to have a slow response. Could you do something to the front end to speed that response up by letting your turbo run, faster all the time, and then having the wastegate at the end?
Yep, you can, and there's a lot of ways to do that. Unfortunately, when you are doing that, you are causing as bad a problem trying to push air through here as you have when you try to pull air through here. So if you're letting it spin, that means you're still doing work over here. And there are actually systems like this wastegate here, that do the same thing but do it here, and they just recirculate. But those are, in general, less efficient than this. This is the most efficient way to do it. And so the question becomes, can I be fast enough with the highest efficiency system to be acceptable? If I can, then I'm going to do this. If I can't, if I need more response time, faster response time, and I'm willing to give up a little efficiency to get there, then I can go do exactly what you're saying, and I can go to that plan. But the reality is we can get there today by doing all the things I mentioned, being smart about the way we modulate this stuff and do that and the other thing, yeah. But there are systems today that do that, that allow it to happen. Anything else? I'm ready to get out of here. All right. Okay, so EPR systems. Let me redraw a little bit, and then we'll be done. Where did I put it on the table?
To your left.
Oh, yeah, there you go. Okay. Oh, take this dude out. Take this guy out. We'll leave that EGR in there. Okay. So, our first, second, and third generation systems, or our EPR systems, have what's called a mechanical mixer. Okay, I'll try to draw this in here. I'll just draw it over there. Okay, and this guy's going to come up in here. Okay, this is called the mixer. Okay. EPR, electronic pressure regulator. Fuel. Air. Okay. All right. That's it. Okay, so the mixer. Mechanical carburetor, okay, sits right here. Takes air in, air actually goes, I guess it actually sits like this. Air goes in this direction, fuel goes in this direction. They combine and come out the bottom here, so that's the flow path as we're going through here, okay. This thing has moving parts in it, okay. It's got a big diaphragm inside, that's what you see here on the edge. And when that moving part moves, the one I just pushed on, it's like a coupled valve, okay? As it moves, it lets more air in, and it also proportionally lets more fuel in. So when this guy's all the way down, like it is right now, there's no flow path for the air or the fuel. They're cut off, all right? And as soon as it lifts, as soon as that thing moves upward, it allows air to flow, and it also allows fuel to flow. And those move in conjunction with each other so that the ratio of the two flows is controlled. So remember phi? Okay, remember the air-fuel ratio? Remember all that? Okay? This guy's mechanically trying to achieve some air-fuel ratio through there. All right? Now, the one thing I can make it do different things with is I can control the pressure of the fuel that's going in. All right? And so if I drive in more fuel pressure, I can make it run richer. I can make the air-fuel ratio go down, all right, or phi go up. If I put in less pressure, I can make it run leaner. I can make phi go down. I can make the air-fuel ratio go up, all right? So mechanically, I can manipulate, electronically, I can manipulate what it wants to do inherently mechanically. That's where EPR comes in. So EPR, this boy right here, okay, is an electronically augmented pressure regulator. Okay, back in the day before EPR, what you'd have is you were missing this whole upper section. This is the electronics package up here, okay? It was just this bottom section, it was just a mechanical regulator. So the way the engine would run is the fuel would come in and be regulated to a fixed pressure all the time. Then it would go into the mixer at a fixed pressure, and it would govern the air to fuel ratio to a fixed value all the time. There's nothing you could do about it. And that was just fine if you wanted to run your engine without a three-way catalyst running at perfect phi=1 stoichiometry and everything else. Okay, it had a bunch of slop in it, it's plus minus 10%, whatever. Run your engine down the road, okay? We got to have massively higher precision to get all our systems to work. Remember, we're running right off the lean misfire limit or off the misfire limit with EGR. And this thing completely doesn't work if you're more than plus or minus 0.1% away from where it wants to be. So this thing is amazingly persnickety about what it wants to come through it. That 99.5% efficiency, that occurs in a band of plus or minus 0.05% of air-fuel ratio, okay? And so if you go astray 0.1% either way, this thing is 96% efficient instead of 99.5. Well, that doesn't sound like much. That's 8 times worse, okay? So that's where we came up with this idea. Okay, this guy allows us to essentially have fuel injector-like control of what used to be just a mechanical system with about 10% slop in it. All right? So what are the advantages? What's the big deal here? Why did we do this instead of just going straight to CFV? This works really, really well. Okay? This is a really good system. First thing it does is it mixes the air and fuel like no other. Okay? Even CFV, the CFV system with the injection nozzle, this is better. It's an awesome homogenizer. Okay? Now, the injection nozzle is good enough, but this is actually better for homogenizing the air and fuel as it flows through. Second thing is when we entered the industry, there was a big concern about electronic reliability. They're coming from purely mechanical engines, okay? This thing, you can yank the power out of it, and it'll just go back to being a mechanical regulator, and you can get home. It'll be puking emissions, but you can drive it home. It'll be drivable. So that was another factor influencing us to go this way. This is a second generation piece. The third thing is, it's just easier. It's just freaking easier. This guy has a pressure transducer on it. All it does is make sure the pressure coming out is right. This thing does the rest. It's simple. Okay? CFV required a lot more development. Okay? Over the full dynamic range of the engine, from idle all the way to full power, full speed, we get a very precisely plus or minus 2% control of the mass flow coming out of this thing. That is a whole nother challenge relative to what we have to do with EPR technology. EPR technology, all we need is precise pressure control. And by the way, this guy provides 2 different devices that combine, that marry up to achieve the same dynamic range on the engine from idle to full power. This guy's moving and this guy's moving. He's changing pressures, this guy's changing positions. Anytime you have 2 devices moving like that, that makes the accuracy requirement of either one much less, okay? And so what you see on CFV is that again. We got a pressure stage on the front and we got a position stage on the back. Same concept, okay? But more execution required, okay? This is a very simple single piece moving device. This is an entire electronic closed loop position control, Hall effect sensed, needle, sonic, man, okay? So those are the reasons. That's why we went the direction we went. There were a lot of factors along the way. So, does that all make sense?
I think it's worth discussing engine pulsation.
Very, very good. Okay, so engine pulsations. When this engine rotates, there's not really a continuous flow of air going in this engine, okay? Intake valves are opening, pistons are moving down, intake valves are closing, and then a repeat on the next cylinder, okay? The fewer cylinders that you have, the worse this is, okay? If you had a 20-cylinder engine, which they're out there, all those events are so overlap each other so much that they all just kind of smooth out into what essentially looks like a very continuous flow. On a 4-cylinder engine, or forget that, how about a single-cylinder engine? Imagine a single-cylinder engine like a lawnmower engine, okay? Every 2 revolutions, for a half a revolution, the intake valve opens up and sucks in a bunch of air, and the intake valve closes, and then nothing happens for another 1.5 revolutions, okay? Those things have amazing pulsations in the airflow. It goes crazy flow, no flow. Crazy flow, no flow, okay? Massive pulsations. 4 cylinders are better than a single cylinder, but not a whole lot better, because each one of these events is actually separated completely from the other, if you think about it, on a 4-cylinder. Quarter revolution, I mean a half revolution, half revolution, half revolution, half revolution. All right, so they're very big pulsations. 6-cylinder is way better. 8-cylinder is really good. Okay, so what happens? This poor little guy is sitting up there. He's a mechanical diaphragm moving thing. Okay, all right, and he's got mass. All right, and he's sitting up here. Remember, and I said, remember when there's no airflow, he's closed. And once the airflow tries to go, then he has to open to allow it to go. All right. So what you actually see, if you could have a slow motion video of this guy on a 4-cylinder at low speeds, is this thing's just going, trying to keep up. All right. And when it does that, because it has mass, and because of the inertia of the airflow stream going through it, it doesn't do a very good job of doing what it's supposed to do. It's really a continuous flow device. Okay. It works well on 6 cylinders, works even better on 8 cylinders. When everything kind of gets slower and less pulsy and smoother, it works really, really well. 4 cylinders, when you go wide open throttle and the pulsations are maximized, big problems here. So we were highly challenged to effectively apply this on 4-cylinder engines. We can do it, but it's a real calibration nightmare. And you got to really work around the inherent nasty dynamics of this thing on 4-cylinder engines. Most of the engines are 6 cylinders, thank goodness, but a few are 4 cylinders. This guy right here is completely unchallenged by pulsations. The reason is it uses supersonic or sonic flow, which means that you reach the speed of sound of the fuel flow down in here, and anytime you achieve the speed of sound, you become immune. In fact, you become completely isolated from anything that happens downstream. So remember, this guy flows into this airstream right here that's pulsating, right? He didn't care. There's a sonic wall, a shock wave, that stands in between all the inner workings of this guy and what's going on that engine downstream. So he literally becomes completely immune to all those pulsations. So this solved a number of problems for us. You know, it's just a step up in technology, and with that you get benefits. So, yeah. Anything else? Yeah, Tim.
You said that the mixer on a 4-cylinder has worse pulsations at wide open throttle or at low?
No, wide open throttle, because when you open the throttle up, what happens is you allow the engine to drink in a larger quantity of air. In fact, this actually acts like, you're an electronics guy, Tim. This acts like a resistor, okay? And so you form a bit of a low-pass filter when this thing is pinched off, okay? When you go wide open on this thing, you got no resistor, you got no low-pass filter. And it's doing some radical stuff, yeah. So you don't take advantage of the capacitive nature of this intake manifold. This intake manifold is the capacitor, that guy's the resistor.
So even though the pulses are coming faster,
Well, they may be coming the same speed. If you open the throttle from at 1,000 RPM fixed, and you start closed and you open, those pulsations grow. So the worst case condition is when you're wide open throttle at any given speed.
And a big key to it is the mixer's more exposed to it. You don't have your resistor.
Yeah. And they get better, typically, not always. They get better at higher speed, but not always. Because what you have is you have tuning effects inside this manifold. So there's kind of second order effects. So you start to get wave propagations that go back and forth through the runners, and you actually can hit a tune point. So it may actually look not so bad at 1,200 RPM, and so you go up to 1,800, you think it's going to improve, and right at 1,800 in a 100 RPM band, it gets really, really, really bad. And then you go 1,900 RPM and it gets really, really good. So you can hit these tuning points in here where these waves are coming back and forth and just causing all kinds of pulsations in the manifold. An intake manifold is not a calm place. It is a very, very pulsy type place. Yeah.
And is designed for cruise speed?
Designed for peak power typically, or peak torque. Yeah, actually peak torque. So designed for peak torque in a lot of cases. Yeah, the tuning of the manifold is. Yeah, of the runners and everything. Yeah, and the bigger the manifold, the better. So again, this is the capacitor, this is the resistor. So if I have a massively huge intake manifold, I can get rid of all those pulsations really nicely. And when that manifold gets really tiny, I get terrible pulsations. Yeah. Yeah. So we've talked about all the complicated stuff that's going on in the engine system, and I've just sketched this in here, but this isn't really what happens, right? Fuel doesn't magically appear at whatever device we have. And this is true for the EPR or the CFV, okay? It doesn't magically appear. Something's got to happen between whatever tank package we have on the vehicle and this point. Two radically different equations, okay? So compressed natural gas. So here's a CNG tank, 3,600 PSI up to, okay? And of course it bleeds down the whole time you're using fuel, but it can be up to 3,600 PSI and it's just depleting the whole time you're using fuel. Very high pressure. On an EPR system, we need, in fact, for a CFV system. So for this device, which is the EPR right here, or for a CFV, which would also similarly sit right here, we just need roughly, I'm going to say 100 PSI. Okay, it's not exactly accurate, but ballpark. Okay, we need about 100 PSI here. Okay, so on a CNG system, how are we going to get there? We're going to use a device called a high pressure regulator. And I don't believe we brought one in here. We didn't. We make a device called a high pressure regulator. HPR. Okay. That is a mechanical device purely. Takes this super high pressure, or what could be the super high pressure over here when you first fill up, and steps it down to 100 PSI. Two-stage regulator. Purely mechanical device. One of the challenges of an HPR is that methane is a really good refrigerant, like Freon. Okay? Has a really high Joule-Thomson coefficient. So that means, what that means is that when you drop pressure on natural gas, it comes out really, really cold. And by really, really cold, I mean negative hundreds of degrees Fahrenheit, potentially. Okay? Depending on the flow rate and how high pressure you have over here on the left. So actually it's just depending on that, but the heat rejection. So one of the challenges of an HPR is keeping it warm while it's flowing lots of horsepower, all right? So typically what you're going to see is you're going to see some lines on the HPR that come back over to the cooling system, the radiator coolant system lines on the engine, because that's good hot 190 degree Fahrenheit fluid that we can use to add heat back to keep this refrigeration effect from freezing up everything in the HPR and downstream. Okay? So that's CNG. Any questions on CNG? All right. LNG. Our system runs with both, remember? Liquefied natural gas. So I'm going to kind of go through a roundabout way of doing things here. I'm going to have the fuel coming down. So the first thing that happens on LNG is we add some heat. Heat exchanger. Okay, that's usually part of the tank package. And it usually just gets heat from the ambient air, because ambient air is so much hotter than the negative 260 degree crud that's in here, okay, that you can just use ambient air to add heat, all right? So we add some heat, and then we do some other stuff. I'll come back up here. And then we have a regulator here, mechanical regulator. We'll call this a topping regulator. This is a topping regulator. Okay, pure mechanical device. This tank, by the way, is going to range from about 60 psi up to about 200 psi. Okay, from about 60 to 200 psi. We're going to add some heat. We're going to come in here. Remember, we want about 100 psi over here. Now, the beautiful thing about EPR is it has no problem getting down to 60. It'll take 60 and run full power all day long. CFE, we had to work hard on to get it to run down there and even below, but it will run there. The high end, once it gets over, say, 100 psi or 85 psi, that's the job of this topping regulator. Okay, so this topping regulator will not allow more than whatever you set it for, 85 or 100 psi, to come downstream. Okay, so if this is 200 psi, this is going to knock it down to 100. It's all good. So fairly straightforward systems. Are there any questions on that guy? Okay. The only other device that we haven't talked about is what's called the lock-off solenoid. Okay. Both EPR and CFV, you will find another device right here. Another little valve, okay? Lock off. Okay? That is a on-off, not proportional, full on, full off, only two modes of operation, bubble tight, leak proof sealing device. Okay? So when you turn the key off on the engine, you shut the engine down, this guy closes, seals up, so that no fuel can flow down here and make its way back out into the air cleaner and into the ambient air. Okay? As soon as you turn the key on, opens up full tilt, lets everything work. Okay, so it's just a shut-off device. And that's present on both the CNG and LNG systems. That's another device we make. All right, any questions on the fuel system? All right, we're done.